Hi everyone. In this video, I'll be discussing how we can build the lakehouse architecture on AWS. Whether you are a data scientist, business analyst, or an application developer, understanding the lakehouse architecture will benefit you in terms of efficiently deriving the data insights. The content is inspired from a blog available on AWS. It's called Build a Lakehouse Architecture on AWS. You can find the link in the description of this video. To understand lakehouse architecture, we must understand the key component of it, which is data lake. Let's answer the first question. Why do we need the data lake? Data from various sources is moved to the data lake, which serves as a single repository for the data analysis across multiple sources. Data in data lake is ingested in all the forms, be it structured, semi-structured, or unstructured. Data lake is best for storing all types of data at scale, supporting various analytics use cases, including big data projects, machine learning models, and real-time analytics. Even though for many organizations, data lake has become the single source of data analytics, it's not able to replace the data warehouse technology, which has been existing from quite long. And there are valid reasons for it. So let's understand why do we still need a data warehouse. Data warehouses are designed to handle complex SQL queries for analytics with high performance and efficiency. In contrast, querying large volumes of raw, unstructured, or semi structured data directly from a data lake can be much slower and less efficient. Data warehouses typically contain cleaned, transformed, and validated data in the structured format. In contrast, data lakes store raw data, which typically lacks the data quality and reliability. Data warehouses are designed to store historical data in a structured format, making it easier to perform time series analysis, trend analysis, etc. Last but not the least, data warehouses are generally more accessible to business users and analysts, unlike data lakes, which are more focused towards the data scientist. In my opinion, this is one of the important aspects for lakehouse architecture. So let's understand this better. Skill sets of the BI users consuming data warehouse is way different than the data analyst or the scientist consuming the data lake. BI analysts have expertise in BI tools like QuickSight, Tableau, etc., along with SQL for creating dashboards and reports. Whereas data scientists deal with machine learning or big data platforms like SageMaker, EMR, Spark, etc. For a typical BI user, directly querying a data lake will require additional skill sets and expertise. Now that we are convinced that we need both the systems, let's understand the challenge associated with the coexistence of these systems. Enterprises need to move data between data lake and data warehouse. For instance, clickstream data from web applications can be collected directly into the data lake, and a part of that data can be moved out to a data warehouse for daily reporting, let's say. This is typically termed as inside out data movement. Similarly, enterprises also move data in other direction. For example, they can copy query results for sales across products and regions from their data warehouse into the data lake, which can help to run product recommendation algorithms using ML. This kind of data transfer is termed as outside in. As data in the data lake and data warehouse continue to grow, it becomes harder to move all this data around. And this is called data gravity. As the skill sets of the BI users versus data scientists is very different, they cannot switch to other systems for querying, which further adds to the challenge. Lakehouse architecture tries to address this challenge. The lakehouse approach helps to connect your data lake and data warehouse into a coherent whole. Here are the 5 key features of a lakehouse architecture. With this, enterprises should be able to build a scalable data lake, build a data warehouse solution specialized for the structured data analysis. They should be able to move the data seamlessly between the data lake and data warehouse and vice versa. We should be able to scale both the systems at low cost without compromising on performance. And at last, the architecture must provide the compliance via a unified way to secure, monitor, and access the data. Keeping these features in mind, AWS divides the Lakehouse ecosystem in 5 different layers. The bottommost layer represents all the data sources, the databases, file systems, streaming sources, or even the applications. The second layer from the bottom represents the ingestion mechanisms. For both data lake and data warehouses, the data can be ingested in batch or the streaming mode. Lakehouse storage layer represents the storage layer where both the data lake and data warehouse are providing the unified storage. To build data lake on AWS S3, the simple storage service is an excellent option for multiple reasons. S3 can effortlessly scale to store and manage petabytes or even exabytes of data. S3 offers high durability. S3 provides cost effective storage solutions with intelligent tiering, infrequent access, glacier, etc. It provides comprehensive security features. It supports storing any type of data, whether structured, unstructured, semi structured, and it provides several tools for data transfer and ingestion into S3. Additionally, it can be integrated with a broad set of AWS services like Athena, Redshift, Glue, EMR, SageMaker, etc. To build the data warehouse on AWS, Redshift is a compelling choice. It uses standard SQL to query the data. It's designed for high performance on large scale datasets. It uses columnar storage, data compression, zone maps, massive parallel processing, and many other mechanisms to boost the query performance. It can scale to support up to petabytes of data. Cost effectiveness, security, integration with AWS ecosystem comes by default, as is the case with S3. Additionally, it provides zero ETL and data sharing features which support querying across multiple systems without moving or copying the data. As we know that the data movement is a challenge between the data warehouse and data lake, there is only one way to access the data for both the users. We must come up with a layer which can be accessed in a way so that a cross data store query processing is possible, which means a BI user can refer the data across data warehouse and data lake in the same query, and this platform should be able to process the query seamlessly. And the same capability even the data lake user should have, which makes him or her capable to query the data present in data lake and data warehouse. And this is what is represented in the layer 4, which is the processing layer. As both the BI user and the data scientist have different skill sets, this layer must support both SQL based processing and the big data based processing. SQL processing is achieved with the help of Redshift Spectrum. This is a feature with Amazon Redshift that provides the capability to build a lakehouse architecture on AWS. Redshift Spectrum provides a unified SQL interface that can accept and process SQL statements where the same query can refer and combine datasets hosted in data lake as well as data warehouse. With Spectrum, queries are executed across multiple nodes in a separately managed infrastructure, which can scale out to process data across petabytes in S3 very efficiently. It can read data that is compressed using open source row or columnar formats, including JSON, CSV, Avro, Parquet, ORC, and Apache Hudi. By reducing the need to transfer large datasets from S3 to Redshift for analysis, Spectrum simplifies the data management and architecture complexity. Big data processing, which enables a similar interface from a data scientist perspective, is implemented with the help of Apache Spark, which can be run on AWS Glue or Amazon EMR. AWS Glue provides the built-in capability to process data stored in Amazon Redshift as well as S3 Data Lake. Spark-based data processing pipelines running on Amazon EMR can be used alternatively. Spark's built-in readers and writers can be used to handle data lake hosted datasets, whereas the open source Spark Amazon Redshift connector can be used to directly read and write the data in Redshift Data Warehouse. Another important aspect of Lakehouse architecture is the catalog layer. This layer is responsible for storing business and technical metadata about the datasets hosted in Lakehouse storage layer. The catalog is shared by both the data lake and the data warehouse and enables writing queries that incorporate data stored in data lake as well as data warehouse in the same SQL. As the number of datasets grows, this layer makes datasets in the lakehouse discoverable by providing search capabilities. In our lakehouse reference architecture, Lake Formation provides the central catalog to store metadata for all datasets hosted in Lakehouse, whether it's on S3 or the Redshift. Redshift Spectrum as well as AWS Glue jobs can refer both Redshift and S3 hosted data in a unified way by accessing them through the common lake formation catalog. To summarize our discussion, here are the different layers and technologies which can be used to build lakehouse architecture. Lakehouse storage can be built with S3 and Redshift. S3 serves as the data lake storage, whereas Redshift serves as the data warehouse. Catalog layer, which is also the part of lakehouse storage, can be built with lake formation. In the processing layer, SQL-based processing will be implemented with the help of Redshift Spectrum, whereas big data processing can be implemented with Apache Spark running either on AWS Glue or EMR. We did not talk about the real-time analytics processing component in this layer, which can be achieved with the help of Amazon Kinesis and Spark Streaming. I did not cover few other components and technologies just to simplify the content for this video. You can explore the blog to get complete details on this topic.